Yes, so our next speaker is Nikki Arendse, who seems to be drifting further and further north. You see her master's here, then her PhD in Copenhagen, and now is even further north. So curious to see where you will end up. But right now she is in Stockholm University at the Oscar Klein Center, and she will continue discussing basically the meaning of some of these tensions.
Thank you, Hank. So yeah, it's very nostalgic for me to be back in Groningen again, and also to be presenting in such a beautiful conference venue. And I think my talk fits quite well after Tamara's one, because I'm going to explore some of the alternative models that have been proposed to resolve this tension, and then in particular the Hubble tension. But because I also want to maximally exploit the fact that we're in such a beautiful dome, we're going to start with a small mini full dome show. So we're just going to go over to Alessandro in the back for the full dome visuals. Yes, so let's set the stage with the expanding universe, because that will be the focus of my talk. Okay, observationally, of course, we can see this because the galaxies are moving away from each other, and the further they are apart, the faster they do so. So let's continue to our perspective on Earth now. So as observers from the Earth, we can detect this expansion of the universe by measuring the distances and redshifts to astrophysical objects around us. Now, initially, we were only able to do this for the solar system and the Milky Way, but as we got better and better telescopes, we were able to travel further in time, and we will also do so in this small journey through the universe. So in the beginning of the 1900s, most people thought this was all there was, that the Milky Way was the whole universe, because we could see all the stars in the Milky Way. And there were also some extended sources that they called nebulae, and these were believed to be clouds of gas and dust in our own galaxy. But then Edwin Hubble discovered that in these nebulae, there were actually individual stars as well, just like in our galaxy. And one particular type of star was very special, Cepheid variable stars, which are pulsating stars where the pulsation period scales with their intrinsic luminosity. And this allowed us to make very precise distance measurements to these stars. So when he did so for the Andromeda Nebula and some other nebulae, he discovered that the distance to them was actually so far that they could not be in our own Milky Way. So they were their own galaxies. Then Edwin Hubble and George Lemaitre also measured the Doppler velocities of these newly discovered galaxies. And they discovered that almost all galaxies are moving away from us. And indeed, this scales with how far they are from us. So this was the discovery of the expanding universe. It was really a groundbreaking discovery. Edwin Hubble got all the credits, so this present-day expansion rate of the universe is called the Hubble constant, or h0. And his initial estimate of the Hubble constant was, as Tamara showed in her plot, around 500 kilometers per second per megaparsec, which we now know is quite far off, and we have gotten much better at determining precise measurements of the Hubble constant. Because as our telescopes got better and better, we were able to see further in space and see more galaxies, which also had different types of standard candles, type 1a supernovae, and they explode at a standardizable luminosity. So we could use them to extend our distance scale even further. And when these type 1a supernovae are combined with Cepheids, this provides a very precise measurement of the Hubble constant of 1.3%. Now, we can even look further into space to the very first light, the cosmic microwave background radiation, or the CMB. Beautiful. So here the colors correspond to tiny density and temperature fluctuations in the early universe. And when we look at the characteristic scales of these spots, this allows us to calculate cosmological parameters, so also the expansion rate of the universe. And thereby this provides a second avenue of calculating the Hubble constant in a very precise way as well. Now let's play this. So when we compare these two different approaches of calculating the Hubble constant, we have the one using the CMB and the local objects, then there's one crucial difference between the two. The CMB method, it allows us to calculate these parameters at the time when this light was released, which is the epoch of recombination. But then, in order to get the present-day expansion rate, we need to assume a cosmological model to extrapolate these parameters to the current time. So that's why the CMB method is model dependent, and they use our standard LCDM model, so dark energy, cold dark matter. On the other hand, the local measurements, they don't need to assume a cosmological model because, so next one, because all the data points of the local measurements already map out the shape of the expansion history of the universe, there's no assumption needed for a cosmological model. So that's the main difference between the two. And of course, we've heard already about the outcome of these two measurements. So let's just play the next part. The CMB results, as obtained by the Planck team, give a lower value of H0 of 67.4. While the local measurements, the next one, give a higher value. So this is performed by the Shoes team using type 1a supernovae and Cepheids, and they get a value of 73. And this discrepancy between the two measurements is really a big outstanding problem in cosmology, because it also calls into question the LCDM model that is used in the CMB analysis. So now we can move back to my own slides. Perfect, thank you. Okay, so the outline for my talk, we will be assessing whether new cosmological models are able to resolve this Hubble tension. So this will be in the form of extensions to the standard LCDM model. And then we'll also briefly take a glance at a new way to get an independent measurement of H0 by using gravitationally lensed supernovae. And the work that I will present here is mainly done in collaboration with Radek Wojtek, Adriano Agnello, and Dugas Kodiramana. So first, to get a bit better into the Hubble tension, we actually need to take a look at another fundamental cosmological parameter as well. And this is the sound horizon. Tamara already mentioned this. It's a distance scale in the early universe. And this originates because in this early universe, the protons and neutrons are in the form of hydrogen and helium, and they're ionized, so there are also free electrons that are floating around. So any photons in this early universe, when they try to travel through it, they're constantly absorbed and re-emitted by these free electrons, such that essentially they're bouncing around instead of traveling in a straight line. So they really clump together to form this photon baryon plasma that has some interesting properties. So let's move to the full dome again for the sound horizon animation. Great, so here we have this photon baryon plasma, and here we can see an overdensity. And because we have a gravitational force directed inwards, but there's also a radiation pressure from the photons outwards, these counteracting forces will then start to oscillate. And this happens at many different scales throughout the universe, corresponding to different sizes of the initial density perturbations. So this process happens everywhere in the early universe, while this is expanding and cooling down, such that at the epoch of recombination, the photons and baryons decouple, the pressure falls away, and at this moment, these structures are frozen in place. So the radius of the largest perturbations is the sound horizon. So these are the perturbations that have just enough time to reach their maximum between the Big Bang and the recombination. And the sound horizon is really imprinted on the universe as it evolves further. So first, the sound horizon is imprinted on the CMB. And we can get the size of the sound horizon from the power spectrum by looking at the position of the first peak in the power spectrum of the CMB. And after the CMB, as the universe continues to evolve, there are also more galaxies and structures forming around these shells because they're a higher density. So we can still see this if we look at the clustering of galaxies in the local universe. And this measurement is called a Baryon Acoustic Oscillation measurement. Great, okay, let's shift back to my own slides. Okay, so these Baryon Acoustic Oscillations, or BAO measurements, are very useful because they don't just give us information about the sound horizon, but also about the Hubble constant. Because if we see one sort of representation of a structure, BAO structure, a shell, then this could either be explained by a low sound horizon in combination with a high expansion rate, so a high Hubble constant, or by a high sound horizon and a low expansion rate. So in this way, BAO measurements constrain the product of H0 and R together. And it means that these parameters are degenerate with each other. So if we see here this Hubble constant sound horizon diagram, then this yellow banana shape is everything that BAO measurements constrain. And we need additional measurements to break this degeneracy. So this can be done by the CMB, which measures a high sound horizon and a low Hubble constant, or by some local measurements that give a low sound horizon and a high Hubble constant. So in this way, the tension is not just the tension in the Hubble constant, it's also in the sound horizon. And in the remainder of this talk, I will regard this combined Hubble constant sound horizon tension and assess whether cosmological models are able to resolve this combined tension. So the first step to do that is to carry out a local determination of both the Hubble constant and the sound horizon. And the data sets used for this in our research are type 1a supernovae, and then these Baryon acoustic oscillation measurements to get the sound horizon. And then these need to be calibrated with something. So generally this is done by Cepheids or stars at the tip of the red giant branch, but these calibrations can only be carried out at relatively low redshifts. And we also wanted to calibrate our data at higher redshifts. So to do that, we used gravitationally lensed quasars, as already discussed by Leon Koopmans in his nice talk. So I will not go into too much detail, but it is a nice excuse to switch to the full dome again for visualization of the lensed quasars. Great, so we can play this. Here we see an overview of these lens systems. So we have the observer, then a massive lens galaxy or cluster, and behind it is a distant quasar. Now, the light of the quasar will be affected by the lens galaxy, and it can be magnified and bent in the direction. So multiple light rays that would not reach us otherwise are converged. And in this scenario, we see two images of the very same object, this quasar. Now, quasars also have slight variations in their brightness over time. And these variations will reach the different images at different moments because they travel a different path and are also affected by this lens potential in a different way. So the next one, if we then have very extensive monitoring campaigns, we can actually observe this difference in arrival time between the images by monitoring how bright the images get. And this allows us to determine this time delay between the images. And the time delay in turn depends on the gravitational potential of the lens galaxy and of a combination of distances between the observer, the lens, and the source, which is called the time delay distance. And since this is a distance, it scales inversely with the Hubble constant, so we can use it to constrain it. Perfect. Okay, thanks, Alessandro. Now we can switch back to my slides to see what will happen if we combine all these data sets. Okay, got it. Yes. So let's see if we combine these results. So first, the calibration done by Cepheids and lens quasars. Here we have the 1 sigma contours for the sound horizon Hubble constant measurements. So when these are compared to measurements from the CMB, then we have this very familiar picture that arises of a very strong tension between the local and the CMB measurements. However, this is not the full story, and there are also local measurements that give a different value of H0. So let's just flash a few over here. So we have surface brightness fluctuations. We also have a different analysis of the same lens quasars by a different group with different assumptions that Leon talks about as well, gives different results, and the tip of the red giant branch measurements. And of course, there are many other ones as well. But the main message here is that the tension is not as clear-cut anymore between local and CMB as it maybe used to be a few years ago. And it's mainly when you consider SHOES and Holy Cow together that you get a strong tension, although currently SHOES itself is also in 5 sigma tension with the CMB. So any new cosmological models are really aimed at resolving the tension in these data sets. And it's important to keep in mind that the local measurements don't require any cosmological model, but the CMB ones do, and therefore they use our standard lambda CDM model. So this then poses the question whether there are any changes that we can make to lambda CDM that can reconcile the tension by shifting the contours of the CMB closer to these local ones. So let's have a look, and first how we can determine the Hubble constants from the CMB in the standard lambda CDM scenario. And this is done by basically comparing the angular and the physical size of the sound horizon. Now, the angular size of the sound horizon, as I said, can be inferred from the power spectrum of the CMB, and the physical size can be inferred from our knowledge of the early universe, because we know the time that has passed between the Big Bang and recombination. We can also calculate the sound speed of the waves, which depends on the density of baryons and photons in the early universe. So this allows us to determine the maximum distance the sound waves could have traveled in that time, which is the sound horizon. Now, when we combine these two measurements, we can calculate the angular diameter distance between us and the CMB. And then using a cosmological model, so lambda CDM, this can be converted into the Hubble constant. And this in turn is discrepant with the local measurements, or some of them. So how can we change this scenario? Well, there are two ways. We can change either the physics before the CMB or after the CMB. So these are sort of the most simple, broadest classes of models that I will discuss here. So firstly, these early time modifications, so before the CMB, how this works is that there's some sort of additional energy in the early universe that contributes to the energy density, which can be in the form of dark radiation or early dark energy. But it has, they have in common that they increase the expansion rate in the early universe. So this shortens the time between the Big Bang and recombination. And also the sound waves can travel a shorter distance. So we have a shorter sound horizon. And we still observe the same CMB, same angular size. So it means that we have a shorter distance between us and the CMB as well, which in turn leads to a higher Hubble constant. The second class of methods, so the late time modifications, so these ones don't change anything before the CMB, only after. And this is done by changing the properties of dark energy. So usually the dark energy density is constant over time, but you can change this by making the equation of state parameter of dark energy smaller than -1. And this allows it to increase over time. So this would lead to a scenario like this, where we have an extra accelerated phase at later times, which also leads to a higher H0. So two different approaches, and the main difference between them is that for the early time modifications, both the sound horizon and the Hubble constant are changed, while for the late time modifications, only H0 is altered. And this is also the crucial difference in how these models work or not, as we will see now. So going back to the comparison of local and CMB data, and here for the local measurements, I've just combined shoes and holy cow as calibrators to give the most extreme interpretation of the tension. So let's see what happens now if we apply the early time modifications to the contours of the CMB. And this is actually what Charlie was asking about as well. This would inflate the uncertainties, right? So let's see. Indeed, uncertainties are inflated, and it does make the contours come closer to the local ones, although most of the time this is not done by shifting the best fit value, just by inflating the uncertainties. And you also see that it's not really enough to resolve this tension. And there's really a limit in how effective these models can be when you still want to maintain a good fit to the CMB data. Then moving on to the late time modifications. Since these ones can only change the Hubble constant, you see that the contours can only move to the right like this. And this is therefore not a solution to this combined Hubble constant sound horizon tension. Even though many models have been put forward as very promising solutions to the Hubble tension, but this is not taking into account other data sets. So can new physics solve the Hubble tension? Well, if this new physics is in the form of these simple modifications of lambda CDM, and if we consider the combined Hubble constant sound horizon tension, then late time modifications are not able to resolve it. Early time modifications can reduce the tension, although most of these models also predict a larger amount of clustering in the local universe, which then actually increases the other tension that Tamara mentioned in sigma 8. So this is another bad side effect of these models. So I think from this, it's also important to take a bit of a look more from the data-driven side instead of the theory side, Because if we have more independent measurements of the Hubble constant and the sound horizon, then this allows us to classify how big this tension problem actually is, or if there's maybe some systematics. So for the remainder of the talk, I would like to quickly go over lensed supernovae as a potential new probe to infer the Hubble constant. So the idea is very much the same as with the lensed quasars, but now we have a supernova behind the lensed galaxy instead of a quasar. And there are some slight differences in their properties, which makes them more or less easy to use. I don't have time to go into all of them, but of course you can imagine that since supernovae are transient phenomena, it can be quite difficult to detect them before they fade away. And indeed, as of now, we've only discovered 3 examples of these lensed supernovae. So it's very difficult. Why is it so difficult? Well, mostly because the current transient surveys that we have, so the ones that really scan the sky, such as the Young Supernova experiment, which is carried out at the Pan-STARRS telescopes in Hawaii, they're not able to see deep enough and with high enough resolution to actually resolve these separate images from the supernovae. So here is an example of simulation of a normal supernova and the lensed one. And as you can see, they look the same because you don't see these multiple images. So it's quite tricky to resolve this. In order to help with this problem, we've developed a pipeline using machine learning to distinguish between large simulated data set of lensed and unlensed supernova images. And especially if we combine the full-time information of these images, then the results are quite promising. So in these current surveys, it would allow us to maybe in the best case scenario find a handful of lensed supernovae a year, really just a few. But this is about to change drastically with the next generation telescopes, such as the Vera Rubin Observatory. So the LSST, which will be carried out there, is expected to discover several hundreds of lensed supernovae a year. So this is really a massive increase. And it means that lensed supernovae are at a very exciting time, and we need to be ready to really harvest their full potential. And because of that, we also started another project to infer the Hubble constant from simulated lensed supernova images to be ready for the real ones when they come out. And the idea why you can do this is because if you have an identical lens system, such as the ones over here, then the one in a universe with a higher Hubble constant will have shorter time delays. So by measuring this, you get information about the Hubble constant. And it will be interesting to see if LSST, which is usually promoted as a discovery machine, so we discover a lensed supernova, we do follow-up, and then we do the cosmological analysis with that data. But we also wanted to see whether LSST data by itself could already provide useful estimates on the Hubble constant. So very quickly, here's an overview of the pipeline that we use for this. It's a 3D convolutional neural network where the inputs are time series of images, so stacked behind each other, such that the third dimension corresponds to time. And then this CNN infers both the lens properties and the time delays from the images, which are then converted analytically into the time delay distance and the Hubble constant. And this, of course, would only give you point estimates of the Hubble constant. So we use a simulation-based inference to estimate the full posteriors. And this is broadly said, this is done by looking at the scatter in the H0 predicted versus the ground truth value. So very quick, just flashing some very preliminary results. So take this with a grain of salt. But this is sort of what it looks like when you combine many of these. So each system by itself doesn't have a lot of constraining power, but then if we still have a large sample, we can still get a decent estimate of H0. But I have to say here that in the newer simulations, we include microlensing and a more realistic cadence, so this will still change quite a bit. But more interestingly is actually to see what other information you can get from this, which is, for example, looking at the uncertainties. So which parameters that go into the analysis contribute the most to the final scatter in H0. So you see that this is the time delay and the source position for doubles or the image position for quads. And if we know all these parameters and how they contribute, then this can also help us to make choices about follow-up observations, because we can then know what information we need to really improve the results. So summarizing, lensed supernovae will be a very promising probe to get new independent measurements of H0, so independent of the CMB and the distance ladder. And in order to help with this, we developed some tools to distinguish lensed and unlensed supernovae and to infer the Hubble constant from lensed supernovae. So hopefully when we combine this view of sort of looking at the theory side, but also having a more data-driven approach, we can hopefully shed some light on this Hubble constant sound horizon tension. Thank you.
Thanks. See. Yeah, I think Charlie has a question. I don't.
When you talk about a 5 sigma tension or a 3 sigma tension, and yet you have 2 ovals, each of one has a separate sigma. So which sigma are you talking about? Are you adding them in quadrature?
Yeah, so we take sort of the integral because it's in 2D. So also sigma, it's a bit differently defined. So we say like for the measurements that it's still like the same percentage is contained as in 1D, if that makes sense.
Okay. You showed oscillations, presumably during radiation domination, that then when you go into matter domination, they then get frozen into the mass distribution. But isn't it the case that these oscillations are on different sizes in this micro background, and therefore you not only have one sound horizon, it depends on the sizes of the objects that are going boom, boom, boom. Yeah. And is that, so and yet you're talking about one sound horizon, and yet don't you have RS and RS over 2, RS over 4 to deal with?
Yeah, definitely. So also if you look at the power spectrum, maybe I have some backup slides. Okay, very small one here. But yeah, you definitely see all these other peaks as well corresponding. So the first peak is the first compression of the wave. So this largest signal from the sound horizon.
Right. But my question is, when you look at the current overdensities as a function of spatial distances from each other to extract RS, you are including the RS over 2, RS over 4 that you get from these bumps. Or am I misunderstanding something?
That's the Fourier transform, but just a single arc.
That's the Fourier transform.
Yeah, that's an L space.
I think you don't get it from the actual objects, but more from the correlation function.
Yeah.
Same as here.
So you're not finding an object and looking at it.
I know that, but you should have correlations on a large scale from the large things that are going. They're caught at different phases at radiation matter equality, and because they're caught at different phases, they will then have different correlations, as you mentioned, from those different sizes, and it's not just one size. Oh, okay, well, that's fine.
So actually, so you showed, because I think that was the first time I saw it this way, so the different H0 versus RS, and what struck me, but it wasn't completely clear how correlated these different measurements are, because if they're really independent, what was striking is that the CMB results look basically in the trace of where the degeneracy direction, which I think is probably something telling us something that right, because it's not necessarily the case that it's really something we're missing there, right? So because I think if it's different physics, as you sort of show, things can move any direction, but the fact that these two measurements lie in the extension of the others, I think this is rather suspicious, or am I misinterpreting that?
Do you mean the supernova and BAO measurements, or?
Yeah, and then with the CMB, so you were showing the different H0 plots, also the lensing, and right, the lensing plus BAO has a degeneracy direction.
You mean that they're all in the same degeneracy direction? Yeah, this is because I used all of them in combination with the Baryon Acoustic Oscillations data set. So then it just aligns them exactly in that degenerate direction. Yeah.
Some time ago, when we were basically in the Groningen group trying to find voids, I spent some time with Erwin Platten, who was the student who did this, looking for the residual voids, i.e. from the holes in the microwave background, which were the biggest voids you could find. And at a conference in Estonia a few years ago, I actually showed a picture of what we found, which showed the largest voids around 100 h to -1 megaparsecs. I always thought it was a little bit flaky, but it seemed like a pretty good idea. Again, this is following Charlie's idea. You find that object now because voids are unequivocal things which have swept everything aside, and the amplitude's quite big. So I don't know, somebody could try that. I tried it, but with Reen and various other people, Erwin.
Do you mean to match the voids that we see currently to the ones that you see in the CMB?
For example, but the biggest voids, because the biggest voids are guaranteed, you can't get voids which are bigger than the sound horizon. So the biggest ones are actually very well defined. So it's actually the statistics of the biggest object taken from a distribution. So it's order statistics.
Yeah, so it's another standard ruler in a way.
Yeah.
Yeah, that's really nice. It's a good
Well,
idea.
it didn't work. I mean,
Okay.
yes,
Maybe
mean,
now.
it was too, I said it was flaky. Otherwise, it would have been published.
So I'm afraid we have to break for coffee, but of course, that's also a good moment to continue any discussions, questions. So I'd like to thank the speakers of this morning session. And well, I guess they'll